cosecant and cotangent curves.
I was blessed.
Greetings. How are you? All right, so shut up. We're going to talk about the secant, cosecant, and cotangent. We kind of, I know the bell rang yesterday, and I continued finishing up in that video with an example. So if you go watch that once I get it posted, it'd be a good idea. But I'm going to do another example very similar to it today with you. But remember, if we want to develop that curve right there, we're really not going to deliberately try to draw that curve initially, okay? We're going to use something else we already know to get it. Does that make sense? And what curve do we use to develop the secant? Yeah, we're going to use the cosine. So plot the cosine first. All right, and the cosine of x is going to look like that thing, okay? So we graph the red curve, and then we start to see that there are some similar points that are being shared by these two curves, right? Okay. If I were to just ask GeoGebra to give me the extremum, so the local and maximum minimums of the sine and cosine curves. So there's the, I guess, the sine or the cosine curve. If it gives me the maximum minimums of that curve as A, B, C, D, and then I ask it to give me the extremums of the secant, you see that they essentially repeat themselves, right? You start to get letters on top of letters, right? Okay, which means that those points are shared. So a maximum or a local maximum for the red curve is actually a local minimum for the purple one, right? Does that make sense? And that all occurs because, you know, at that point, when we have 0, 1, okay, on the cosine curve, then 0, the reciprocal of 1 should be on the secant. Well, the reciprocal of 1 is just 1, so we should have 0, 1, 0, 1 on both curves. Is that all right with everybody? Okay. Now the same idea should be played out right here. Okay. At let's see here, get my x-axis in terms of radians. Okay, when I look at a measurement of pi over 2 on the x-axis, okay, that y value is 0 right there, correct? Well, what's the reciprocal of 0? Undefined, right? It does not exist, okay? So what we end up with there at pi over 2 is an asymptote. We get another one at 3 pi over 2. Get another one at 5 pi over 2, and so forth. We're going to get one at negative pi over 2. We'll get one, oh, we got to put x equals, let's go x equals a then. We'll get one at negative 3 pi over 2, and those are all x-intercepts of the sine curve, right? And what those asymptotes do is kind of restricts your secant curve inside, and they act as any other vertical asymptote would. You cannot cross over them, right? Okay. So in the event of graphing the purple one, what you're going to do first is actually graph the red one. Okay. Find the maximum minimums of the red one. Find the x-intercepts of the red one, and that gives you all the tools, all the necessary information to graph the purple one. Is that something we can do? Okay. Now, what I want you to understand is that the sine curve is just a horizontal translation of the secant, or sorry, cosine curve. Does that make sense? If I take that red curve and move it to the right, pi over 2 units. Okay. So let's just say take the cosine and move it to the right, pi over 2 units. Oh, to the right, Gives me that there, right? Okay. So let's take everything else and move everything else to the right, pi over 2 units. And then move my asymptotes, pi over 2 units. Move that one, pi over 2 units. So it just gives me 2 pi over 1. Okay, and that one I had defined weird. Move this one over to pi. X equals negative pi. We'll have one at x equals 0. Okay, and we don't have that one. Okay, but we start getting that curve, right? Well, what is the red curve? That's the sine function now, right? Okay, and I've got it defined differently here, but the sine, if I typed in sine of x, it puts it right on top, make it blue here, puts it right on top of the last one we had, right? Okay, so the sine function. So then if that's a sine function, what is that curve? What is the purple one? It's the cosecant. If I graph the cosecant of x, okay, and let's make it that color, okay, we see that it is developed essentially the same way, right? Take the sine value, take the sine curve, okay, on its x-intercepts, you have asymptotes, okay, and then the maximums and minimums on the sine curve become maximum or minimums on your cosecant curve, right? And we graph those two things using the sine or cosine, right? So secant and cosecant are developed off that. Is that all right with everyone? So that stems to the question, or gets us to the question, I guess, of how do you deal with graphing something like, and this is what I was saying was at the end of yesterday's video when you guys left. How do I graph something like y equals 2, I don't know, let's go cosecant of 2x plus, let's just go pi. Something like that, okay? How do I do that, okay? And my argument is that you're not really deliberately going to focus on cosecant, okay? The easier thing to do is to rewrite this so that it is 2, and now what is the reciprocal of cosecant? Sine. Now I'm going to take the 2 out as well, to take that b out. So it looks something like that, okay? And I'm going to graph that blue curve. And we'll find everything out that I need about that blue curve. And once I graph that blue curve, I should have the maximum minimum of that blue curve, which then turn into be maximum minimums of the red one, right? And we'll find the x-intercepts of the blue curve, because that's going to provide me the asymptotes of the red one. And then I've got all the things I need to graph the red one. Does that make sense? Okay. And the reason we do this is because we spent, a majority of last week trying to graph some of those things, and spending time on how to graph the sine function transformed. So as we do this, obviously that's going to be your amplitude, right? So my x-axis and my y-axis, let me fix that. Let's go put that back into my integers, okay? So my y value for the sine is going to go from -2 to +2. That's my amplitude. The sine starts here, right? Okay. Now what is that number going to do to my period? 2 pi over b. It's going to change my period to what? Pi. Okay. So I know my sine function is going to start here at 0, 0, and it's going to finish at pi. Normally it would start, if there wasn't a b value here, it normally would start at 0 and finish at 2 pi, right? But now our period is pi, so it's gonna stop there. Now halfway in between, we know that it goes through the x-axis again. And we should have then points there and there. And those are at that's pi over 4 and 3 pi over 4 there. And we should have those points for, right now, the sine function. Okay? However, there is still this horizontal shift, right? How far am I going to move each one of these points? Yeah, pi over 2. That tells me right there I'm going to move it pi over 2. Which direction? Left. So this point here is going to move to there. This point here is going to move to there, which would be negative pi over 4. Okay, that one is going to move there. So it's kind of on top of one that has already been moved, right? It's kind of weird, but whatever. This one here is going to be moved there. And this one here is going to be moved to there. Okay? Now, I know maybe mine were blue. Yours are probably all gray, right? You're all using pencils. When I do this with a pencil, if I graph, before I do any left or right movements, like I'll use dots, but then when I want to transform them, I want to move them, I'll put X's over the top of the ones that are getting moved. Does that make sense? Because then I'll have, for instance, here I've got red ones that are on top of old blue ones, right? So you would have X's on top of old dots. And that might help you realize which ones you need to connect to get your sine curve. So right now I'm going to connect just my red ones. So that right there is it's one period of 2 sine of 2 times x plus pi over 2. And if we put the whole thing in there, you see that we did do an accurate job of coming up with that curve, right? Or at least one period of that curve. Okay? And you could, once you have what I've got written up there in blue, what I drew, you could take the relationships, the kind of the symmetries that exist inside those 5 points, and you can paste them to the right, you can paste them to the left, so you get that entire orange curve. Is that all right with everybody? Okay. So that orange curve right now is y equals 2 sine of 2x plus pi over 2. Okay? We didn't want to graph that, right? We wanted to graph y equals 2 cosecant of 2x plus pi over 2. Now that I've got this one here, I've got this orange one, I can now say, well, for the blue one, there should be an asymptote at x equals negative 3 pi over 2. There should be one at x equals negative pi. There should be one at x equals negative pi over 2. X equals 0. X equals pi over 2. You keep doing these as many as you need. But I get all those asymptotes, right? Inside those asymptotes, is there a maximum right there? So is that going to provide me a minimum for my cosecant? Inside these two asymptotes, is there a minimum there? So that's going to provide me a maximum for my cosecant. And I can keep doing that however far the problem tells me. It might tell me to do, 2 complete periods. It might say do 1 complete period. It might tell me to graph it between a certain interval. Okay? But we start getting those curves, right? And those curves then are, if we put all of them in, should be those purple. Now, I didn't do a great job because mine are kind of a little bit too flat at the bottom, but they are in the right spots. They at least have the right minimums and maximums. And now we have a start to that entire curve, 2 cosecant 2 x plus pi over 2. That's something that we can do. Would you agree that it's no different than what we've already done maybe last week with graphing? It's just adding 2 steps, adding the asymptotes, and then drawing from those maximums or minimums of the sine curve or the cosine curve towards those asymptotes, and then start following the behavior that any curve would towards a vertical asymptote. All right? Okay. So, like I said, you can do that with secant, you can do that with cosecant. It does not matter. All right. Let's see here. All right, now that we've got that, let's talk about one more curve. We haven't talked about this one at all yet, and it's going to be the cotangent. So let's just we can either use the tangent curve to do this, or we can use the unit circle. I think maybe it's more obvious to maybe use the unit circle to come up with these. And you can use the unit circle. We didn't do it to find the secant and cosecant, but if you wanted to use the unit circle to do secant and cosecant, by all means, that can be done. You can go find your asymptotes. You'll find your coordinates appropriately and all that kind of stuff. But let's just do the code. We're going to work on finding the cotangent here. So if I have this point right here, which is 0 radians, right? Okay. The ordered pair would be 1, 0 right there, correct? Okay. Well, if we think about what cotangent is, it might be even better to think initially what the tangent is. Remember, tangent of theta is y divided by x, correct? So what's cotangent? Yeah, x divided by y. Okay. So let's take 1 divided by 0. What's 1 divided by 0? Undefined. So at 0 radians, you have a vertical asymptote for the cotangent function. Okay. Now I'm going to keep going around and find some just useful values like pi over 2. That ordered pair is 0, 1, right? So now what is x divided by y there? 0. So that is a value that we can have. So we're going to plot pi over 2 as the x value, and then x divided by y, or 0 divided by 1, as my y value. So there's a point on your cotangent. Okay. I'm going to go over here to pi. And that's negative 1, 0, right? Okay. Negative 1, 0. So if I take x divided by y, what's that give me? Undefined again. So x equals pi. You have another asymptote. Okay. We can go down to 3 pi over 2. It's going to be 0 divided by negative 1. So at 3 pi over 2, we have another ordered pair at 0. So 3 pi over 2 comes 0. And then I get back up to 2 pi, which 2 pi is the same thing as what 0 was, right? 0 radians. There was an asymptote at 0 radians, so there better be an asymptote at 2 pi. And that's just one cycle going, counterclockwise around the unit circle. If we go clockwise, we should end up at an asymptote at x equals negative pi. X equals negative 2 pi. So we should have asymptotes at those locations. Now, you don't need all of them right now. Maybe the only 2 that you really need are 0 and pi. Because then you see that if I keep adding pi to the last asymptote, it'll give me a new one, right? Or if I start at 0 and start subtracting multiples of pi, it gives me the asymptotes to the left. Now, we do have some key points in here that were useful, okay, pi over 2. But I need more than 1 point in inside this, because right now I don't know, does my graph, I know it's going to be behave in regards to these asymptotes. Is it going to do something like this? Because that'd be one option. That would be another option, right? Or it might do something like that. Or it might do something like that, right? So there's a lot of things that it could do in between those two asymptotes. So we got to kind of figure that out. Well, it'd be nice to have other points then, okay? Well, isn't there a really nice point on the unit circle that is, I know it's kind of hard to see here, but right there on the unit circle, and that's pi over 4, right? Now, I consider that a nice value because when you take x divided by y, because that ordered pair is radical 2 over 2, comma, radical 2 over 2, right? When you take x divided by y, what do you get? 1. So at pi over 4, you get a y value of 1. Well, in between these two asymptotes, or between 0 and pi on my unit circle, isn't there another point over here on my unit circle that's really nice? And that's 3 pi over 4, right? 3 pi over 4. The y value would be radical 2 over 2, but the x value is negative radical 2 over 2. So when you divide those, what's your quotient? Negative 1. And now you have those 3 ordered pairs, and now you get the idea that really if I start at A and I start moving left, I can only go up. Okay? Now you could say, well, what if you jump back down? Well, we could start finding more and more points that are closer and closer to 0, and we'll find out that we do move up there. And as I move from A to the right, I'm going to go through D, and then I'll go that direction and try to hug the asymptote that way. And then if I look, and I'm just going to graph over the top of this what the cotangent looks like. That set of black curves is the cotangent from negative infinity to positive infinity. You see it's periodic. He's doing the same exact thing over and over again, right? Okay. Now those were similar to the points that we found on the tangent function, right? Okay. We had y values of 1 on the tangent function, y values of negative 1. We had some x values that were interesting on the tangent function. If I were to look at the tangent, just kind of superimpose the tangent function on top of this, it's going to get kind of messy, but tangent, put that in there. Put the tangent function on top of there. Okay. So the tangent function, let me color it a different color. All right, so the blue one, okay, is the tangent function, right? And you kind of see how the blue one and the black one, or the blue one and the gray one, they kind of go in different directions, and they really have different starting points as well. I don't know if that's the best view of this. Let's put them side to side. Let's look at, let's see here, graphics 2. All right, so this one over here is the cotangent. If I put the tangent on this one, okay, and you see then that they kind of have different different behaviors, but they do have some kind of a similar pattern, don't they? Look at where this asymptote here is at 0, right? On the cotangent. On the tangent, that's an x-intercept, isn't it? This asymptote on the cotangent is at pi. Over here on the tangent, it's an x-intercept, right? Okay. And that all occurs because on the unit circle, think about this, on the unit circle for the tangent function, let's look at pi, okay? That would be -1, 0, right? Well, for tangent, that's y divided by x, so it's 0 divided by -1. But on the cotangent, which is the reciprocal of this, right? Okay, at pi, at that spot right there on the unit circle, the cotangent is -1 divided by 0. And we know that we can't do that. So everywhere that we have an x-intercept on the tangent, you're going to actually have an asymptote on the cotangent. Does that make sense? Okay. And you see as well that this x-intercept here, the x-intercept here for the cotangent is actually an asymptote over here for the tangent. Okay. So there's some direct correlations, direct links between the two. Knowing though that they start, their fundamental period's going to start in a different spot, right? If I look at just the parent functions of both these, let me just delete all that out there. Let's just go the cotangent of x. We usually look at it between 0 is less than x is less than pi. Okay, so that is the initial parent function with the asymptotes x equals 0 and x equals pi. Okay, that's what we look at for the cotangent. And if we can take that and cut and paste it, we'll get the rest of the curve. For the tangent, remember the tangent, we look at an interval between -pi/2 less than x less than pi/2. So then our asymptotes are x equals -pi/2 and +pi/2. Okay? So you do see, hopefully, that they are, the fundamental periods are a little bit different, right? Where they start, one starts at 0 and goes to pi, the other one starts at -pi/2 and goes to pi/2. Okay? And then the cotangent, which is the one on the left, we refer to it as being as always decreasing, right? Okay, so we call that monotonic. Okay, and the one on the right, the tangent, is always increasing, also monotonic. But that's the behaviors of those two curves and how they relate to one another. Does that make sense, everybody? Okay. Let me take real quick before we leave here. Let's take that cotangent one, or the tangent one, doesn't really matter. Let's take the tangent one. See if I can bring up the algebra here. If I take the tangent one, and let's say I multiply out front by a negative. Okay? Does that start to look a little bit more like that one? But now it's not centered in the same spot, right? This is having an x-intercept of 0. This one's having an x-intercept of pi/2. Can I take this one and move it to the right pi/2 units? Okay, now when I move that to the right pi/2 units, I should move this interval from the same amount. So moving that pi/2 units to the right should give me 0. Moving this pi/2 units to the right should give me pi. And now do we see that those two things are indeed the same then? Get this thing centered a little bit better. Okay. So the cotangent of x and the opposite of tangent of x minus pi/2, those are the same graph. Okay? So we have different ways of maybe identifying cotangents. Does that make sense? Kind of like how we were able to say sine to write sine in terms of cosine, or cosine in terms of sine, by a movement of pi/2 left to right as well. We do the same thing with tangent cotangent. Hey, I moved the homework assignment that was due today, I moved that back to tomorrow, give you one more day on it. And 6-4 is not due till Friday. You're welcome.
Thank you.